In 2002, 71 people lost their lives because a plane physically couldn't climb fast enough to avoid a collision. It was fighting a wall of its own creation called dirty drag, a violent wake caused by traditional flaps that make emergency maneuvers impossible. That drag isn't just dangerous, it's an invisible tax. It forces engines to work harder, burning cash and dumping unnecessary carbon dioxide with every single landing. Enter AeroLattice, a technology we created to solve this exact problem, forcing airflow to stay smooth, silent, and safe.
First, our ram air inlet captures high-pressure energy from the aircraft's own velocity, forcing it into our core innovation at the carbon peak gyroid diffuser. The unique topology of a gyroid acts as a mathematical flow conditioner, forcing turbulent air through thousands of splits and recombinations, homogenizing it into a uniform pressure field. A hydrophobic graphene oxide membrane then scrubs this air, capturing harmful pollutants to clean up the environment while ensuring the core never clogs. Finally, the stable air bleeds out through this microporous titanium skin, creating a high-energy jet sheet. Instead of the airflow detaching from the steep curve to create a chaotic, turbulent wake, this jet energizes the boundary layer, forcing the flow to adhere to the surface and suppressing dirty drag at its source. To validate this, we went to the first principles. With the Navier-Stokes equations being too complex to solve for such a shape, we modeled the gyroid as a Darcy-Forsheimer resistance tensor, deriving its key geometric constants like permeability or K. Solving the final energy balance proved this generates a momentum coefficient of 0.035, exceeding the critical threshold for flow reattachment. The math confirms that our project works. And now for the physical proof. The key to our system is the gyroid's ability to distribute pressure evenly. I'm going to inject a concentrated blast of air into a single point on the intake, and you see uniform distribution. This gyroid took a single point of pressure and spread it across the entire surface. That's how we created the stable, even jet sheet that destroyed dirty drag.
To validate this, we used a professional simulation engine called OpenFOAM. Used by companies like SpaceX and Airbus, OpenFOAM uses computational fluid dynamics to simulate real-world airflow and turbulence. To measure the changes in air pressure caused by our porous structure, we used a virtual wind tunnel to simulate a 30-degree angle of attack, which causes a critical stall point in landing for our solid baseline and AeroLattice. The solid baseline created more lift but generated dirty drag. Meanwhile, our lattice sacrificed a small amount of lift to bleed pressure and clean the airflow, cutting drag by 17.9%. This shows that it functions as a high-efficiency stabilizer, prioritizing fuel savings and structural relief over raw force.
While competitors exist, they miss the mark where it counts. Winglets are excellent for cruise but useless during the critical high-lift landing phase. Microvanes are passive band-aids that actually add parasitic drag. Future concepts like Airbus's Clean Sky 2 are decades away and offer no retrofit path for today's fleet. AeroLattice stands alone, the only retrofit solution that targets landing drag with active control. Our go-to-market strategy employs a three-phase beachhead approach. AeroLattice is only installed during scheduled C-checks, which are mandatory heavy maintenance visits every 18 to 36 months, creating zero additional downtime for airlines. Our first phase enters through cargo carriers facing the highest fuel and night noise pressure, then expands to low-cost airlines such as Ryanair, Indigo, and Southwest, driven by cost per available seat mile reduction, and scale through aircraft lessors, enabling fleet-wide deployment. Our $2.6 billion total addressable market is based on 27,000 active commercial jets, with a $1.8 billion serviceable addressable market focused on single-aisle aircraft that fly frequent short-haul routes. We target 5 to 7% penetration of this market, or roughly 950 to 1,300 aircraft, generating approximately $95 to $130 million in retrofit revenue over 5 years. We generate revenue through a hybrid model, a $95,000 one-time AeroLattice retrofit kit per aircraft, paired with a $1,000 per year in SaaS software for fuel, noise, and compliance analytics. Southwest operates roughly 800 Boeing 737 aircraft, flying thousands of short-haul flights per day, making it an ideal full-fleet retrofit candidate. Retrofitting the fleet would generate approximately $76 million in a one-time hardware revenue, plus $800,000 in high-margin recurring SaaS revenue annually, while delivering a 7 to 9% fuel reduction that translates into hundreds of millions of dollars in lifetime fuel savings for the airline.
We plan to start with freight carriers to prove the value of our technology, scaling to $29 million in revenue by year 3 as we expand to commercial airlines.
Our initial sales will be driven through aviation accelerators, MRO partnerships, and industry conferences where airlines evaluate certified retrofit technologies. Retrofitting Southwest Airlines' 800 plus aircraft would eliminate roughly 240,000 tons of CO2 annually, which is the equivalent of removing about 50,000 cars from the road, just achieved through a simple flap retrofit.
We worked with MIT's Aviation Lab and FAA's CLEAN program in order to validate against strict ICAO environmental standards. To launch this product in the aviation sector, we will get the FAA Supplemental Type Certificate and get validation from the EASA.
I'm Sidh. I'm Shiv. I'm Parthiv.
And I'm Svaran.
Join us in redefining aviation efficiency with AeroLattice.